Okay. Good afternoon, everyone. Thank you for being here again. I'll have a couple of announcements before we finish off with the numerical differentiation. Clearly, the big elephant in the room is the exam 2 next Thursday. So remember that. I posted some documents for you on the front page today, like a review, study guide, and review and practice exam from the handwritten type. But exam 2 is going to be similar in spirit to exam 1 with much less essay questions, which makes me want to brings me to the exam 1 question. I really apologize for this kind of inexcusable delay. I actually had to regrade. Anyway, it's a long story. Hopefully exam 2, you'll get your grades immediately after. With exam 1, I'll be done with them by end of day tomorrow, so you'll get your grades by end of day tomorrow. Interestingly, and this is anecdotally, I haven't done any quantification yet, but the vast majority did better on the essay questions than the multiple choice ones. I don't know, maybe it's because you have more flexibility in explaining yourself, expressing what you want to say, rather than having a narrow selection of choices. But exam 2 is going to be also longer. It's going to be 1 hour long with 2 attempts. So you have a more relaxed way of taking it, and you'll get to use the full effort of the 2 attempts. And this is based on the mid-semester feedback, which I also thank you for providing. It has been generally positive. I really appreciate the feedback that you've given. One of the items I want to bring up is, I'm a very active person. I like to walk around and talk and gesture. And in a class this large, it's sometimes difficult to hear each other, especially with the masks on. So, if you're okay when you're kind of answering a question or asking a question, if you would take off your mask so I can hear better. I do have hearing loss in my left ear, and I'll let you ask me how that happened at the end of the semester. That's like a long story. But it kind of complicates with a large room and noise in the background. It makes it difficult for me to sometimes hear with the mask on. So I would ask you to take off the mask. Anyway, so we can hear each other better if you're comfortable with that. If you're not, we'll figure out a way. Exam 2 next week, exam 2. So next Tuesday, we'll spend time on doing a discussion on exam 2. And I'm also answering the muddy points on regression. And I just issued a graded survey for muddy points on numerical integration and numerical differentiation. Some of the questions there are really, really good and important questions. Okay, so they help me fine-tune how I'm explaining things, but sometimes there's no way to cover what might be a gap in your understanding of the material, or what might I have skimmed over something that I assumed you already know. So those muddy points I think they're super useful. They take some time to answer, so I hope to have them ready for you by next week, by this weekend and next week, and I'll post them as soon as they are available. There's like 48 questions on the regression alone. But study those very carefully for the exams. I mean, I hope you noticed that exam 1 had many of the questions that were asked on the muddy points, on linear solvers, etc. So please do spend some time on studying those, because they do target some particularly useful questions and gaps in our understanding of the material. Okay. Do you have any comments, concerns, feedback? All right. So here's the plan for today. We'll finish off with numerical differentiation. Oh, for this assignment, I'm going to give you a couple of days extension, because there is one slide. I mean, it's an obvious slide, but I feel like I owe it to you to at least go over it before you do the homework. that does the higher order differentiation for one-sided higher order differentiation. So I'll go over the slide, but I'll give you 2 days extension on the assignment. That is going to target problem 1 specifically for the flying saucer. Okay. I know most of you haven't done the homework yet, but you'll appreciate the 2 days. Okay. So, all right. So last time we kind of skimmed over this slide. Let me adjust the lighting. Okay. Okay, not enough to sleep. Okay. So given a discrete set of data points, and we always represented the data as like these equally spaced, at least in this case, equally spaced points with independent variables, the xi's, and dependent variables, the fi's. And then we said in the middle, we could use second order central discretization to compute the derivative, okay, for f. And at the endpoints, because you only have data on one side, we said you would use either the forward difference on the left or the backward difference on the right. We explained that the issue with this in this case is that you're mixing orders, excuse me, which is not always a good idea. You're using second order in the middle and first order on the ends. Your error might propagate and contaminate your solution. We'll see in the next slide how to improve how to get a second order forward and a second order backward difference. But given this situation, central in the middle and first order forward and backward on the ends, we didn't do this activity last time. We're going to do that today on that notebook with gaps. So please pull it up. We're going to take the COVID-19 data. Okay, we're going to parse it, plot it, and then compute the rates, essentially the rates of infection. And I'll show you a little trick how to do an entire data set in one shot with a vectorized operation in Python. So you don't have to do a for loop over each point and compute its derivative and then next point. You can do the whole thing by slicing through the entire data array. Okay, so go ahead and pull up your Jupyter notebooks. I'm going to remove this slide because the question is clear now. Okay. Right. Let's see. I'll zoom in a little bit. How's that? Perfect. Okay. I need to re-execute this notebook. Okay. Activity 2, develop a Python code that to find. Excellent. Develop a Python code to calculate the first derivative of discrete data and apply the code to analyze the COVID-19 cases. Your code should use central differencing for interior points, forward and backward for the first and last points. And to be more specific, first order forward and backward differencing for the first and last data points. So first, we're going to import the COVID data. You can take this as is. I'm just using NumPy load text. You'll probably learn more about pandas and data frames later on, but this is kind of one of the simplest ways to load up a data file. I know the data, what it looks like. All you have to worry about is that this gives you an X data set and a Y data set for mainland China in blue and the world in orange. Now, this is outdated data, very old, but it kind of still illustrates the point. Okay, you can apply it to current data. Okay, let me comment this out. I want to save a PDF. Okay, so okay, what I'm showing here is YICH is YI China. Those are the cases in China. Okay, the XI is simply the time days since the outbreak. Okay, and I create that using just a numpy.arange, just like an integer lin space, if you want, from day 0 to however many days have been recorded. And YI world, so those are the data for the entire world. Okay, they're put in the array YI world and they're plotted over here. Okay, So I hope this is clear. I'm plotting YI China or data, the cases in China as a function of the number of days since the outbreak, and the cases in the entire world as a function of the number of days since the outbreak. Okay. So now I am asking you to define a routine called df by dx that only takes xi and fi data. So it takes the array of independent variables and the array and an array of dependent variables. And we're assuming that spacing is constant. So you can compute delta x as the difference between any two x values. Okay. So xi1 minus xi0 gives you a delta x. And I initialize my result to a NumPy array of zeros that looks like fi. So essentially, it's of the same size as fi, which is a pretty smart way to create an NumPy array without having to figure out the size of the other array and how big it is. It's just you can use NumPy.zeros like fi. It creates an array full of zeros that looks like fi, so the same size. Okay, here's the trick. Here's where you're gonna spend some time. Okay, at least at this one in the middle. So result 0, that is gonna contain the derivative at the first point. Okay, use forward difference for the first point and use backward difference for the last point. Remember the inverse indexing. Now for all the points in the middle, I have this line over here. So let me explain to you result 1 to minus 1. What does that mean? That slices my result array, okay, to take only the interior points. Remember, result 0 has the first data point and result minus 1 has the last data point. I can access all the points in the middle simply by slicing that array. This methodology using the semicolon is called slicing. Okay. I slice through the array from the second point to the point before last. So let me give you an example. Again, if you are in doubt, print it out. Okay. So let's consider, for example, we're going to create an A. I'm going to call A is numpy.array. Scroll up a little bit. Numpy.array. And I'm going to put in this array 0, 1, 2, or let me make it less, let me make it more useful. So 22, 33, 42, 34, 431, 29, and 7. Okay. Now, A0 is going to give you 22, correct? You're accessing the first entry in this array. Now, A minus 1, we expect to give you 7, correct? The last point in the array, because you can index backwards. Minus 1, minus 2, okay? So A minus 1 is going to give you 7, and A minus 2 is going to give you 29, okay? Now, what if I put A1 to minus 1? This defines a range to take a subset of this array. It slices through the array. It starts at A1, so this point, and doesn't go to A negative 1. It goes to A negative 2. Okay, so it gives me 33 to 29. Okay, because it is an open bound on the right-hand side. Okay, so when you do this, this is what you're going to get. 33, 42, 431, and 29. So if you think of your result array for the derivatives, first point, interior points, and last point, this is what this is doing. It's telling me I want to fill in the derivatives in these points in the middle. Now, I want you to use that same idea to compute the derivatives, the central derivative. Okay, and I'll show you the formula using slicing in one line. Okay, so slice the array. Take the f data, you know, the central derivative was fi plus 1 minus fi minus 1 over 2 delta x. So use slicing to slice through the array that way. Okay, to fill in, really, this is going to be kind of the most, the hardest point in this exercise. Okay, I'll give you some time. Here is the formula. So you have your notebook in front of you. Here's the formula for central differencing. Fi plus 1 minus Fi minus 1 over 2 delta x. So think of slicing the array the same way I described. You are looking at this, all the data in the middle, and then you can take subsets of those data to take the data to the right minus the data to the left over delta x. Okay? What do you mean? Oh, you don't put -1. You don't put anything. Yes, the great question, Ryan. Thank you. So your colleague is saying, okay, well, what if I want to include? Okay, so this array gives me the center points. Ryan is thinking, I want all the points to the right. So I want to take all of this from 33 to include -7. So how do you do that? You simply don't put anything here. Great point. Thank you. Okay. So now try to use slicing to implement this in one shot. Look, I'm not saying you cannot do it with a for loop in your homework. I really don't care. Again, I don't care. But this is, using full vectorized operations in Python. Okay. So you want the data to the right of your point minus the data to the left of your point. So Fi plus 1 minus Fi minus 1 over 2 delta x. Try it. Just try it. If you have a question, let me know. And if you don't mind putting your name tags, I'm starting to remember all your names. Yes, it's easier for you to remember one more name for your teachers, but for me, I keep trying to remember all your names. I would love to know all your names by the end. Kimball, any leads? Maybe. Maybe. It works. I should buy name tags for this class. Honestly, but it should be done everyone who has a computer should just get stickers just to put on the back of the that's a good idea. Yeah, but but maybe and I guess you should be able to remove it. Maybe you don't want to advertise your name if you're at a coffee shop, or I don't know. By my name. We'll get a sticker with a folding cover on it and a privacy cover. Looks like you got it. Well, you should do Fi plus 1 minus Fi minus 1 over 2 delta x, right? So this is more like F. This is the data to the left. So switch your. You were working, you were not? Yeah. Yeah, no, thank you. That was a great question. Okay. Do we have any leads on this? Come on, detectives. Any leads? I know some of you got it. Would you like to share? Okay, so let's start with the first one. If I can find my cursor. Okay. All right, so for the first one, fi1 minus fi0, so okay, over dx. Okay, and the last one is it's fi negative 1 minus fi negative 2 over dx. So if you remember the formula, at the first point we got f1 minus f0 over delta x. At the last point we have fi, or the last point, which is fi minus 1 minus fi minus 2 over delta x. Okay. Now this one, Ryan, you said you got it? Yeah. You want to try? Okay. 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 All right. So let's explain why this works. You're right. This is correct. Okay. So what does fi2 to the end give us? So remember, I'm going to take this example again over here. We figured out how to do the derivative at this point. Okay. We figured it out. That's going to result 0. Now for this point, okay, it's going to be, so for result at 1, this is going to be fi at 2 minus fi at 0 over 2 delta x. For this point, for that point I equal 2, it's going to be f3 minus f1 over 2 delta x. What we can do is, for this point, so if you notice, there's a pattern. For this point, we needed this data. For that, we need that data point, and so on. Okay, so we can take the entire set of points, these guys, all of these guys, minus all of these guys over 2 delta x in one shot. So think about it. For point 33, we wanted 42 minus 22 over 2 delta x. For point 42, we wanted 431 minus 33 over 2 delta x, and so on. Now, if you separate that idea, if you look only at the points to the right, they consist of 42, 431, 29, and 7. Those are all the points to the right. Okay? And the points to the left are 22, 33, 42, and 431. So we can take those two subsets and subtract them from each other point-wise. It's going to do it point-wise. That's the key. It's going to take each entry at a time and subtract it from the corresponding entry in the other subset array. And when it does that, it gets you your derivatives in question. It's a pretty neat little trick how to operate with these data. That's why Python is so powerful. So when you do this, we claim that this routine should work for any equally spaced data. Okay, and we're going to apply it here on the data for China and data for the world. And then, we can go ahead and plot that's the rate of change. That's the number of cases per day, okay, for China, which is in blue, and worldwide in orange. And it's huge, okay? So you can probably do a semi-log y to compress that y-axis, okay? So you can see there's like 1,000 cases a day, but like over here, okay? And then as you're like 1 month into the pandemic, as China started getting natural immunity and lockdowns, etc. And then it started spreading across the world. Okay, so now you see the world separating from what's happening in China. Okay, because the infection rates are starting to go really high in the world. Okay, pretty useful, right? Gives you an idea how to calculate the rate of change. Okay. Okay. All right. So here, the last two slides, those are responsible for granting you the two-day extension for the assignment, because we didn't have a chance to cover those last time. You can do the same. You can use the same mechanism we used last time to derive higher order formulas for the derivative. We combine Taylor series I plus 1, I minus 1. You can combine Taylor series at I plus 2, I minus 3, whatever you want. You can combine them together to construct whatever order of accuracy derivative you want, whether one-sided, centered, forward, or backward. Okay. Now, there are some conditions for some of those approximations, and those are going to be specifically whether you have a constant spacing or not. So this is a list of formulas for the first derivative. We studied the forward difference and the backward difference. And for those two, there is no need to have equal spacing in our derivation, because we only used one Taylor series formula, right? One Taylor series, either at I plus 1 or at I minus 1. There's no requirement on the spacing. You could have equal or unequal spacing. It's not going to matter in your data, in your discrete data. Okay. Whereas for central differencing, because we combined the two Taylor series in a way, we had to cancel out that delta x, that second derivative term. We had to assume that h was constant between the two Taylor series, the I plus 1 Taylor series, the I minus 1 Taylor series. Otherwise, we wouldn't have been able to cancel out those derivatives. Okay. And so use of the central differencing requires you to have equal spacing in your discrete data. If you're applying this to compute a continuous, the derivative of a continuous function, doesn't matter, because you can choose your delta x whatever you want. Okay, it doesn't matter. There's no concept of equal spacing for a continuous function. Okay, you choose your delta x infinitesimally small. Okay. Now, the issue we had with the data set we looked at is we use central second order in the middle, but we use first order at the ends. This could be problematic in transport type problems where you have fluid flow or heat transfer. The same way that fluid and heat moves information, moves heat, moves mass around, it's going to move your errors around as well. So it's a bad idea to mix second and first order approximations in problems that have heat and fluid flow and mass transfer. Okay. So we need a solution to get high order forward and backward differencing, okay, at the endpoints. And these are the formulas for those. Okay. For a second order forward difference, you start using at point I plus 1, and point I plus 2. You're further reaching into the domain. Same thing with backward differencing. If you're at the end of the domain, you go to Fi minus 1 and Fi minus 2. Okay, and you can get a second order backward difference formula. Okay, to derive this formula, these formulas, just do a Taylor series for Fi plus 1 and Fi plus 2, and do this combination, and you're gonna see you get a second order approximation for the first derivative. Okay. Now we can apply the same strategy for second derivatives. Okay. Again, so that evaluates f double prime the same way we evaluate f prime. We can use the Taylor series to extract out f double prime from the Taylor series and do combinations. The algebra gets very tedious. We can derive linear systems. There's a whole theory about that. It's not the purpose of this chapter to do this. However, these are very handy formulas that I reference occasionally, okay, when I need to compute an approximation. But The same way you had first and second order approximations for the first derivative, you have first and second order approximations for the second derivative. Okay. It turns out you cannot do a first order central difference on a second derivative, which doesn't exist always second order. Okay, but you can do first order forward and backward differencing. And just the same way you had the data laid out for the first derivative, you can do it's just an application of a formula. Okay, you want to derive these formulas, just do Taylor series for fi plus 1 and fi minus 1 and combine them in this way, and you'll get suddenly the second derivative is going to show up, and you truncate everything else, you get second order error. But we have the same problem here in that if you have data at the endpoints, you're bound to go to first order forward and backward differencing unless you use higher order forward and higher order backward differencing for the second derivative. You see it gets more and more complicated. Okay, for the first derivative, we only had fi plus 1, fi plus 2. For the second derivative, you need one more point. Same thing here, okay, for the backward difference. Okay, these are for second derivatives. Okay, so your homework problem 1, this assignment.